All right. Let me crack this open. Oh, fuck. Made a mess. Okay. I'm back. We finished. Let's see. I always forget it. I hate that you can't click and, oh my gosh, you can with middle mouse. I'm not the smartest. It's okay. Let's see. We did these. We did doubling the number. All right. Let's do the other byte operations. Yeah. All right. Byte or. May think it's unethical to eat all the earthlings. I didn't mention this before, but I really like the little alien like side story because it's not really a part of the game. It's like the framing tool. It's funny. I think it's funny. I like it. It's cute. You may think it's unethical to eat all the earthlings that don't win the competition. No, that's reasonable. Should do that in real life. Actually, it's okay because you lived good lives in the wild and we don't let the meat go to waste. It's real. Or each bit of the input and output the result. All right. So, hold on, turn my sound up. Just like before, right? It's the same as an OR gate, but we're making it out of bytes instead of, right? So all it is 8 OR gates. Let me actually go ahead and place this. Gonna be enough space. I'm gonna get a little cramped. 1, 2, 3, 4, 5, 6, 7, 8. Actually, what I should have done, let me do that. It kind of annoys me that it doesn't make a sound when you, why did I do this? No, that's this. This is I'm not the brightest. I don't I don't know. I don't know what's going on. I'm panicking. It's fine. This is that I could make this really nice and pretty, but I just couldn't be bothered. All right, so that's horrible. That absolute mess. It's fine. Do it work. Oh, it's running through. It works flawlessly. I now have the byte or onwards. Now same thing but for and. Our previous model of brain size being the main predictor of intelligence was naive. Do they like not have brains? How do they work? Tool making and usage is key in the early evolutionary stage of developing intelligence. Therefore, a number of arms on a creature is clearly the main predictor of intelligence. Do you know there are sea creatures from your planet with 4 times as many arms as you, and they're doing better? I believe. Yeah. Oh wait, no, this is a not. Why did I think it was an and? Oh, this one's easy. I believe that a octopus could finish this game, and I need a biologist, or specifically a zoologist, to get on that. Perfect. Okay, so this, not, as you can see, not's every symbol. So if you take a look at it, right, what it's actually doing, because this is 0, this is 255, which you'll notice is the max. So what it's actually doing is showing how empty, I suppose, the byte is, right? So 64, if you were to ask how much is left, right? How much more could there be? Well, 191. So it's 255 minus this answer. Just if you like math, right? It's kind of cool. Let's test it. Bam, works flawlessly, as we knew it would. All right, now I gotta go do some of these. Half adder. This is when we get into real math. We measure the universe with numbers, so your machine must learn to count. True. Treat the inputs as 0 or 1 depending on if they are off or on. Add them together in binary such that the result is either 0 or 1. As with the normal addition, if the result cannot be described with one digit, set the carry bit to 1. Remember when you're in, yeah, it shows it here. When you're in like grade school, right? You're learning to count, right? 0 and 0 gives you 0. 1 and 0 gives you 1. 0 and 1 gives 1. But if there's both 1s, right? Well, just like if you added 5 and 5 in decimal, right? You'd get 0, but with a carry to 1, making it 10. So this, the sum, you should by now recognize that is just an OR, right? So if we cycle through, it's perfect. But I don't know, there's weird artifacting issues, I think because I'm in the Linux version. But it's fine, probably. And then this is just an AND gate, right? It's just if they're both true. And this is the foundation. Oh, I meant to. This is the foundation of all math in computers. What are they? I need to learn the keybinds to this game. Oh, it's just shift drag. Okay. And this is right click, wire comment, and okay. Anyways, run it. Perfect. I didn't actually get a half adder component, which is sad, but, and then read best, if that's a half adder, what's a full adder? Well, this is. In the previous level, we added together 2 inputs. This time we add 3. Once again, add the input together in binary, such that the result is either 0 or 1. As with normal addition, if the result cannot be described with one digit, set the carry to 1. So the reason for this is, if you remember with the half adder, right, there's 2 inputs and 3 outputs. But unless you're doing math only on bits, like on 1 and 1 bit, right, you're going to want it to feed into the next adder, right, because they got to build a bigger machine. That's the point of this one, right? It is the, do I have the 3 input XOR gate? I do not. But I remember how to make it. Remember that adding 2 XOR gates, this can't go up any higher, gives you, right, these two, that's will add up normally, and then this third one does just the same. And all this is doing is checking if there is an odd number on, and if there is, the sum will be 1. And otherwise, if at least 2 of these is on, right, at least 2, 2 or 3, 2 or more, you could say, then the carry needs to be on. So we got a 3-prong AND just for such an occasion. Beautiful. I've bamboozled myself. That's not how this works. It's this and this, or this and this, or this and this. Oh, can I copy? Cannot. No copy paste. What a shame. Okay. Cool. Okay, so do that same little bus design we did before. This and this, or this and this, or this and that. This last one, we can cut these off to make it fit. Play nice. All right, now it should work. Perfect. And this, we did get a new component, full adder. Outputs 3 bits, or inputs 3, outputs 2. Perfect. And then if you were like adding a byte, actually, hold on, adding a byte is going to be, that's this one. Okay, so we need to do bit switch first. If components output different values on the same wire, you get an error. However, some components have gray output pins. These are not outputting at all when the component is not enabled. This is the case for the bit switch component. When the top pin is 0, the output is disabled. This means that more than one of these gray output pins can connect on the same wire and not cause an error, as long as only one of them is enabled at a time. Using 2 NOT gates and 2 switches, build an XOR gate. Oh, actually just gives us all of our components. I'll just go ahead and place them all. Okay, XOR. So all we're doing is do it like this. But, right, so if this is on, it needs to turn this off. So, and if this is off, it needs to turn this on. So what we're going to do, oops, let's just move, stop it. Can I fit this here? I can. Perfect. I connected these both to the same line. That is because I'm stupid. See, and we can safely connect these two because turn them both on. See, it's perfect. And that's an XOR gate made out of just switches and NOTs. Switches are cool. Oh, and it automatically gives me an 8-bit switch. Nice, I don't even have to make it. If you did want to make it, it would just be, right, you could see how it would work. Adding bytes. Add the 2 input bytes. Each output bit in the output should be the result of the addition of the corresponding bits from the inputs and potential carry. And potentially a carry. If the result did not fit in 8 bits, turn the output carry on. You can think of it as the 9th bit. Finally, there's an input carry as well. This is useful for chaining together byte adders to add large numbers, like we said. You can think of this carry as adding either 0 or 1. Use this and if you get stuck. Cool. So, if you've done a little bit of programming, you know that with some variables in certain languages, right, there's a max amount. Like integers can only be so big. And when you add them, you might get overflow. Or if you're on an old calculator, right, if it gets too big, it suddenly becomes negative. That's what overflow is. That's what byte adders do. So, all we have to do, right, trust the vision. So this carry, right? If we add in 3, right? If these both have this bit turned on, this is 1, right? And this output is 1, right? Yes, it outputs 1, but also this one outputs 1, right? And this carries to this, and this carries to this, and so on. And this last one, the carry goes to the carry output. Then, for the rest of them, it's very straightforward. Perfect. And now, as you can see, 1 plus 1 plus 1 equals 3. 1 plus 5 plus 1 is 7. Turn this off, goes back down to 6. 69 plus 1 is 70. And so on and so forth. Beautiful. Now we have the byte addition. And that is the basic adding component of a computer. Negative numbers. Oh no. To know the difference between things, you need subtraction. To get subtraction, first you need negative numbers. This level introduces the 2's complement, the most common representation for negative numbers. Here, the highest digit is negated. For bytes, this means that the eighth digit changes its value from positive 128 to negative. Finish this level to 3 or beyond. So basically, right, they said, because normally, right, a byte, you could go up to 255 with 8 bits. So all the 2's complement means is you can go from minus 128 to 127. So including 0, it's the same number of options. But this is negative 1. But using these, you can now access a bunch of negative numbers because this first one is negative. Start. What is 1? I already had it. 15 did not change. Minus 1 is everything. Minus 2 is everything but 1. Minus 3. It takes a little getting used to, I will admit. Oh, minus 7. Minus 12. Oh, minus 13. Minus 2. Minus 15. Minus 23. Oh, I had it. Oh, I made it to level 3. It's fine. I didn't do as well as that one as I did on the other one. So that's how negative numbers work in computers. Signed negator. I'm going to do this one. Yeah, I'm going to finish this one and that'll be it for this. This has been the rest of arithmetic. This level you probably want to turn on signed numbers so the highest bit is shown as 128. Oh yeah, if I click up here, it'll switch. I'll explain that. Taking input as signed, where the 8th bit is 128, make a component that takes a number and negates it. For example, 4 negated would become minus 4. Minus 9 negated would become 9. Simple. Now, I have the advantage of having taken enough classes to know how to invert a number. I say that, and then, but as you can see, the difference between signed and unsigned numbers that doesn't actually exist, right? The computer doesn't know. It doesn't care. It's just how you read it. But the way you do the signed numbers is you flip every bit. Actually, this isn't going to be quite right. Oh, I don't even need any of these because I have logic. Flip every bit, right? Turn on signed. So 4, you notice 2 becomes negative 3. 66 becomes negative 67. 82 becomes minus 83. Well, you notice a pattern there, I hope. And we can say, oh, well, if I do that and then just add a 1 to the carry pin, suddenly it's always correct. Just add 1. Flip all the bits, add 1. That's the trick, so to speak. Nope. And that is it for the basic arithmetic. There's some stuff up here with decoders and a actual logic engine, but I'm going to want to get through all this first. So that's it for this one. Thanks for watching. Thanks for commenting, those who did, and see you next time.